Okay, so good afternoon, everyone. Uh, in the previous lecture, we were talking about the bootstrap methods. I gave you the introduction of the bootstrap method, why we need it, and how we use it. So now we are going to talk about the theoretical properties of the empirical distribution, right? And the further procedure of the bootstrap. So here we have the first theorem, that is Glivenko-Cantelli theorem, that given in 1933. So this theorem states that the supremum of x, the absolute difference between the empirical CDF and the exact population CDF, almost surely with probability 0, with probability 1 will be 0 as n tends to infinity. So this statement says that the empirical distribution function converges to the uniformly to the true CDF almost surely. So what is the meaning of this one? So if this theorem says that if you have the distribution function of the population fx that usually unknown, all right, that is unknown, and f and x cap is your empirical CDF, all right, from the CDF from the sample, and supremum x here defined as the supremum of x is basically defining the maximum difference, all right, the maximum difference over over all values of x, all right, so maximum difference over the value of x, and as is basically almost surely, all right. So this theorem states that as sample size increases, the entire empirical CDF get closer and closer to the true distribution curve everywhere, not at just and one particular point, but at all the points simultaneously. For example, if we just take the real life example, suppose I want to estimate the income distribution. All right, I want to estimate the income distribution of people in Trinidad and Tobago. All right. So at that time, I just conduct a survey. Okay, I'm going to conduct a survey of 500 people, and with respect to that, I just calculate the empirical CDF. All right, of 500 peoples. Here it is 500, n equals to 500. Then I will get a one empirical CDF, and then I will calculate a survey of 5,000 people, and I will again calculate the empirical CDF with respect to those 5,000 values. All right. So in that one, and so on. Sorry, and so on. So in that one, what happen as sample size increases for the max at the maximum difference for value x, the absolute difference of empirical CDF and the population CDF will be tends to 0. All right, so that means the sample distribution become almost identical to the true income distribution. All right, so when we collect the more data, So first of all, we just ignore the random fluctuation. All right. And secondly, the empirical CDF will be stabilized, because if you just see here in the 5 observation, when we had the only 5 observation, we were finding some gap between the true value and the empirical CDF here. All right, some difference we were finding, but if you will increase the sample size, this differences you will not find for every single value of x. And the step function here, you see that it is when you have the less number of observation, this is behaving like a step function here. But when you have the large sample, so this step function will approach to the smooth curve, okay, or smooth true CDF. All right, so now we just come to the another theorem, that is the DKW inequality. For every epsilon, the probability of the difference of empirical absolute difference of the empirical CDF and the population CDF at the value of x will be maximum or greater than epsilon. The probability of that will be less than equals to 2 into e raised to the power minus 2 n epsilon square. All right, so this gives us the finite sample bound on how close f cap n is to f. So basically what it tells us, it tells us the probability that the empirical CDF, okay, the probability of the empirical CDF is far from true value. The probability that the empirical CDF is far from true CDF decreases exponentially fast with the sample size. All right. Basically, in theorem 1 says that eventually it will converge, fnx will converge to fx, but theorem 2 says that even for a fixed sample size, here is how close you are likely to be. All right, that is the meaning of that one. For example, for the second theorem, all right, if you just take the example, if you just fix the n, here n is equals to 100 and epsilon is equals to 0.5 you are going to take, then what this difference is basically? This difference is basically the error between, or the bias between the true CDF and the estimated CDF or empirical CDF. So it will be probability that error is greater than 0.1, because epsilon is 1, will be less than equals to 2 into e raised to the power minus 2 into, and we have taken 100 into epsilon raised to the power 2, means the square of the epsilon. So it will be less than equals to 2 into e raised to the power square of 0.1 will be 0.001, multiply with 100, it will becomes 1, so it will be e raised to the power minus 2, and that will be equals to approximately, basically not less than equals to, approximate this one is 0.27. But if in this case you just increase the n is, you just take 500, okay, instead of 100 we are going to take n equals to 500, so it will becomes 2 into e raised to the power minus 2, 500 into 0.1 raised to the power 2. All right, so it will becomes 2 into e raised to the power minus 2 into 5, that is less than equals to 2 into e raised to the power minus 10, and it will be equivalent to 0.00009. All right, so if you just see, I just increased the 400 observations in my sample. It is exponentially decreased. Earlier it was 0.27, now it is 0.00009. That is quite low. All right, so it will exponentially decrease when you will increase the sample size. All right, and the third one is that for a fixed x, square root of n into the difference of empirical CTF and the population CTF will converge under the distribution to normal distribution with mean 0 and variance fx into 1 minus fx. So it says that basically at any fixed value of x, fnx is approximately normally distributed for large n. All right. So now we will discuss about the basic principle of the bootstrap. All right. What is the basic principle of the bootstrap? So in the fundamental idea, what is the fundamental idea of for the simulation study? It says that if you know that your sample size xi follows any particular distribution fx, any particular CDF fx, so you can use different methods of sample generation like inverse CDF method, accept reject method, right, give sampler and others, or MH algorithm that we have discussed previously during the Bayesian inference. So you can use that methods and you can generate your sample size x1, x2 up to xn. All right, you can generate that x1, x2, xn from your given CDF fx, right? So, and then you can find out the estimated value of your parameter theta cap, and you can generate the random samples again and again from this CDF. Okay, again you can use this CDF to generate your new sample x1 star, x2 star, all right, up to xn. If you know the CDF, so you can generate from your population CDF itself. You don't need to generate from your given sample. You can directly go to the your parent population and you can generate the sample from there, right? And you can estimate the parameters theta again and again from that one, and that will provide you the different estimates of theta, theta 1 cap, theta 2 cap, and so on. And from that theta 1 cap, theta 2 cap, you can find out the sampling distribution. All right. You can find out the sampling distribution of your parameter theta. But if we do not know the f, our population CDF, so we need to plug in the empirical CDF. That is your capital F cap NX. All right. So what we need to do at that time, replace the F with Fn cap empirical CDF, and this is equivalent to the sampling with the replacement from the data. So what we are going to do, we are going to generate sampling from the Fn cap is exactly the same as sampling with replacement from the observed data. That will give you many fake data sets that look like the original sample. When I'm saying the fake data set, okay, this empirical CDF will give us the fake data set. Why I'm saying the fake data set? Because if you have the sample that x1, x2 up to xn is a one sample that you have, in that one, in that sample, you will generate the sample again, say x2, x2, x4, xn minus 1, xn minus 1, and so on. This will be a sample of size n again. So this sample is coming from the same sample that you already had. So that's why this sample I am calling a fake data set. But because it is coming from our original sample, this sample is coming from our original sample. So that's why it will look like our original data set. All right. So the distribution of theta cap star for each sample, we will calculate the theta cap star here. All right. So the distribution of the theta cap star across the those fake data sets approximate the true sampling distribution of theta cap. All right. So in the mathematical statement, the distribution of theta cap star minus theta cap give us the, for the given data, will be approximate to the distribution of theta cap minus theta. All right. The bootstrap distribution approximate the true sampling distribution. So now we will talk about the bootstrap algorithm, how it works. So now we are talking about the bootstrap algorithm under the non-parametric inference. All right. This is the method under the non-parametric. All right. Do you understand the meaning of the non-parametric? Any one of you understand meaning of the non-parametric inference or non-parametric data? Any one of you understand the meaning of the non-parametric data? Non-parametric data is our data is called as the non-parametric. Okay, someone replied. Independent of parameters. Okay. Not exactly, we should say that is not the proper definition. Data is called as non-parametric, basically. The proper definition, I just tell you, okay, it has no distribution, correct. So, data set is called as the non-parametric data set when you cannot associate that data set with any particular distribution, right? So, in that one, suppose we already have the sample, one sample we have x1, x2, xn is the sample is given, and with statistic t means statistic t can be anything. All right, t can be anything, mean, all right, mean, median, regression coefficient, okay, and etc. It can be anything that you are going to find out through the this given sample, one sample. All right, and now let b is the replicates, the number of times we are going to replicate. So what we are going to do, from the original data we estimate our theta cap. All right, whatever the statistic we want to calculate, mean, median, mode. Once we calculate that one, all right, so that we will denote as the theta cap. That is our sample from, it comes from our one sample. So after that, what we are going to do, for b, small b equals to 1 to up to b, all right, it b can be around 1000. So first we need to generate the indices I1, B, I2 up to I and B. Okay, uniformly from 1 to n with replacement. Basically, what we need to do, if your data is following some distribution, okay, when your data xi follows some distribution, so you can randomly generate the data from the given distribution. At that time, you do not need to fix the index or the position. All right, because automatically whatever the data will be generated, that is coming from the distribution itself. But here, what we need to do, we need to generate the I from the discrete uniform distribution from 1 to n of size n. All right. So at that time, it will give us index like this. Suppose I am having the data in x 1, 2, 3, and 4. This is my data set. All right. So I need to generate the index I that will give us the position. All right. Like 2, 2, 1, 4. Okay. These are the position. So indexes I need to generate, and with respect to that indexes, I will generate the bootstrap sample x star b, that will be x I1b, xi2b up to xinb. All right, so I will generate the data again and again, and I will compute the bootstrap replicates. Means for every single sample, I will compute the theta cap that I am going to denote by the theta star b. So after that, I will get total theta cap star 1, theta cap star 2 up to theta cap star b. So if I am taking b equals to 1000, so I will get the 1000 values of the theta cap here, and I can, that is basically will fall denotes the distribution, bootstrap distribution of the theta cap. All right, so that is basically non-parametric bootstrap distribution. So here I am having this one, this code. So I wrote a one code here that is in your PPT also. So bootstrap, in the bootstrap, I'm preparing a function, all right, of the data function. I'm creating a function of data and statistic can be anything, mean, median, mode, and I'm going to replicate 10,000 times. All right, so that is my function. Okay, so function is basically of the data and the statistic. Bootstrap is a function of data and statistic. In that one, I am denoting the n, the length of the data that I am going to take, and original state. In the original state, I am going to find out the original statistic of the data, that is either mean, median, mode, whatever I want to calculate. After that, I will generate the B bootstrap samples. That is, B is basically a number of replicates, how many times I'm going to replicate. So before that, I'm going to assign a bootstrap as a null vector, okay, in the numeric B, where I need to store the values of the my sample statistic. All right. So for after that, I am going to apply the for loop that will start that is b in 1 to b. All right, whatever the size of b is there, that is 10,000 I took. So 10,000 times this for loop should run. So after that, what I'm going to do, sample with I'm going to take the sample with the replacement. So in the boot sample, I'm going to generate the sample, okay, of size n. The I'm going to use the command sample to generate the data from the my original data, that is stored in data size of n, and replace is equals to true. Means with replacement, I'm going to take of size n from the data. I'm going to generate the sample. In boot stat b, here I'm going to store my statistic that I want to calculate here, mean, median, whatever I want to calculate here, that should be stored here. After that, I'm going to compute the bootstrap estimates. So it will be boot mean. So if I want to find out the mean of the bootstrap sample, so mean of the bootstraps, whatever the statistic I'm going to calculate. So boot standard error. So standard error I'm going to calculate here through the command sd, and the boot bias. So formula of the biasness, we already know that is the expected value of theta cap minus theta. So boot mean minus original state. All right. So percentile confidence interval. So there are several ways to find out the confidence interval in the bootstrap that we will discuss just after this. So confidence interval for the CI lower, we are going to take the quantile boot stats 0.025, because we don't know whether our data is symmetric or not. So that's why we are going to take the quantile confidence interval. So that is asymmetric. So at that time it will be lower side, it will be 0.025, and upper will be quantile bootstrap 0.975. All right, in the list, I'm going to store all the values: original stats, standard error, biasness, confidence interval, and the distribution that I'm going to check. So after that, I'm going to close the function in that one. After that, I'm going to generate this data. Here, I'm giving the original data, that is 23, 45, 67, 34, and so on up to 65. So I want to check bootstrap for the mean. All right. So in that one, I will just check result mean, that is the bootstrap data, this data, and instead of statistic, it should be mean. All right. I'm going to define statistic equals to mean. So after that, I'm going to call sample mean. Okay, results mean dollar original. All right. So original mean I'm going to calculate here, and then after that I'm going to check the results means standard error. I'm going to call for the biasness of the my bootstrap, and 95% of confidence interval I'm going to call in the result mean dollars CI. All right. So for here, up to here, we just check. I'm going to run the code. So this is the sample mean of my bootstrap method. From my bootstrap method, I just check the mean of my data. Is it visible to all of you? I just increase the size here. So it should be visible for all of you. Mean of data. That is 56.85. That is the same one. So that is the original basically. So bootstrap standard error is 4.153, bootstrap biasness is minus 0.0266, and the 95% quantile confidence interval is 48.7 and 64.95. Now I am going to check it for the median. Okay, I am going to check it for the median. So this is the distribution. Okay, if you just check this one, this blue one, before that, I just checked the median. Sample median is 56. Bootstrap standard error of the your sample median is 7.094, and the bootstrap confidence interval for your median is 44 and 67. All right, and here we have the mean distribution of our bootstrap. Okay, this is the blue one is the bootstrap of our bootstrap distribution of our mean, and the red one is the original mean. So if you will find that in the bootstrap also, again we have the maximum mean near to the our original mean value, right? So that is basically bootstrap method here. So after that, here the formula to calculate the bootstrap standard error, if you want to find out it by your own manually, so that is basically standard error of the boot theta cap equals to square root of 1 upon b minus 1. B is your the number of replication summation. B goes small b goes to capital B. Theta cap star b minus theta star theta bar star. Okay, so mean where theta bar star is your the mean of boot strap theta cap. All right, theta cap star. So this is the formula for your bootstrap standard error. Theoretical justification is that as beta tends to infinity, the empirical distribution of the bootstrap replicates the converge to the sampling distribution under the empirical CDF f cap n, and by the bootstrap principle, this approximation is true. Approximate the true sampling distribution under the population distribution f. All right. So that is your bootstrap standard error for the non-parametric case. Now the bootstrap bias, that is bias theta cap is equals to expected value of theta cap minus theta. So similarly, bias of the boot is theta cap, theta bar star minus theta cap. All right. So that means 1 upon b summation small b equals to 1 to capital B theta cap star b minus theta cap. All right. So bias corrected estimates for that one. The formula is beta cap BC equals to theta cap minus bias cap of the boot. All right. So that is basically, if you just use this one, the formula is theta cap, sorry, theta cap bias corrected theta cap minus theta cap star. All right. Minus, and then because it is minus, so it will become plus theta cap. So it is basically 2 theta cap minus theta bar star. That is your corrected bias. So bias correction can increase the variance. All right. So bias correction reduce the symmetric bias but may increase the variance here. So now comes to the bootstrap intervals, confidence intervals. So to find out the bootstrap confidence interval, if you find out the normal interval, asymptotic normal in confidence interval, so formula is similar to the your asymptotic confidence interval that we already had. Theta cap plus minus z alpha by 2 into the standard error of the bootstrap. All right, that we already had. And for the percentile interval, that is theta cap star alpha by 2 and theta cap star 1 minus alpha by 2 that we used in the our R code. And the pivotal interval formula is 2 theta cap minus theta cap star 1 minus alpha by 2 and 2 theta cap minus theta cap star alpha by 2, that is from your correct bias interval. All right. So bias corrected and accelerated most accurate. So bias corrected interval of the bootstrap is the better one in compared to the normal intervals and the percentile. All right. So here we can define the bias corrected asymptotic confidence interval as that one. Say if you have the probability p theta cap naught equals to that the CDF, empirical CDF that we were taking, theta cap star b is less than theta cap divided by b, and z naught is defined as the empirical CDF of p cap theta naught. So in that one, the accelerated constant is we calculate by a cap equals to summation over the range of I goes to 1 to n theta bar minus, that is your original theta bar theta cap I raised to the power 3 divided by 6 into summation over the range of I goes to 1 to n theta bar dot minus theta cap I square and whole raised to the power 3 by 2. So this is your isolated constant, but here your theta bar is theta bar dot is defined as 1 upon n summation over the range of I theta cap I. Alright. So theta cap I are the jackknife leave one out estimate that is basically comes from the your bootstrap sample. So after that you need to calculate the adjusted probability, that is your alpha 1 and alpha 2 you need to calculate. That will be calculated as alpha 1 is equals to the CDF of Z naught plus Z naught plus Z alpha by 2 divided by 1 minus A cap Z naught plus Z alpha by 2. And alpha 2 is basically the CDF of Z naught plus Z naught plus Z 1 minus alpha by 2 divided by 1 minus A cap Z naught plus Z1 minus alpha by 2. Alright. And A cap is already given there. So the BCA interval is quantile function of with respect to alpha 1, alright, of theta cap star B and Q alpha 2 of theta cap star B. That is will be your BCA interval. Okay, so now we are going to check when bootstrap works. So when you have the smooth statistic means function that change continuously with data, at that time you can use the bootstrap. Regular cases statistics with square root and consistent limiting distribution means where you have the root and consistent limits in the distributions, at that time you can use bootstrap. Representative sample means when the sample captures the population structure properly, at that time you can use the uh, bootstrap. And moderate to large n means generally if you have the n greater than or equals to 20, at that time you can use bootstrap, and bootstrap will produce the better results. All right. Examples of good bootstrap statistic is the sample mean, sample variance, sample median, and quantiles correlation coefficient and regression coefficients. All right. So now when bootstrap will fail, so bootstrap will fail or need the modification in the extreme means when the sample minimum and maximum converge at the rate n, not square root of n. So at that time you cannot use the bootstrap methods. For example, for the uniform, the theta cap is basically the what is the mean, what is the estimates for the theta when theta follows x follows the uniform distribution, that is xn. What is xn? Xn is your the nth ordered observation. All right. So n is not involved here in that one, in that observation. So you cannot use the bootstrap method here to estimate. All right. Or non-regular statistics. So statistics with unusual limiting distributions. So at that time you cannot use that one. Heavy tail distribution if they are going to provide you. So at that time you may need more bootstrap samples, because at that time what happened in the heavy tail, at the most of the sample will lie in the initially, and it will, only few observation will be there in the last. So at that time you need more replicates or more bootstrap sample to get the better results. All right, because here you have the observation in the last, but that observation is not occurring a many number of times. All right, so there is a chance, there is a less chances that it will occur in your given data set, given bootstrap data set again and again, right? So dependent data, so time series data require the block bootstrap. So simple bootstrap method you cannot use in the dependent data, because in the time series what happens, the present observations depends on the your past observations. All right, today's share price depends on the yesterday's closing share price. All right, and yesterday's closing share price was depends on the other days share price. So at that time you cannot use the simple bootstrap method. And third, the last fifth point is very small samples, n is less than 10. So when you have the very small sample or small data set, at that time bootstrap may be problematic to use. All right, so when sample size is very small, at that time we prefer to go to the Bayesian inference, right? So the solutions for that one is m out of n bootstrap for extreme, that is one method that we can use. Bootstrap for the time series that we can use, and subsampling for non-regular cases that we can use for the last. All right. So this is the R code that I showed you right now. Okay. So now we will talk about the bootstrap for the parametric data. So in parametric bootstrap, we assume that data paramet comes from a non-parametric family, say f theta, and theta belongs to the parametric space capital theta, and we estimate the parameter theta cap from the sample statistic tx, and generate the bootstrap sample from the fitted model f theta cap, and we use the bootstrap sample for the inference. All right. So what is the difference in both of them? uh, Non-parametric and parametric. In non-parametric, we resample from the data directly that is given. All right, and in the parametric inference, what we usually do, we just simulate the data from the fitted distribution. All right. So what is the mathematical framework here? So we just take the example that suppose x1, x2, xn follows the are the IID random variables, IID random variables that follows the CDF f theta, where theta belongs to the parametric space capital theta, and that is the subset of the real line. All right. For example, normal distribution, exponential distribution, and gamma distribution, and typically use the MLE. We use the MLE theta cap. All right, or method of moments and match sample moments to the population moments. So in that one, how it will work, the parametric bootstrap. In the parametric bootstrap, we just have the data from the given parametric family of theta, and we compute the statistic t, and we are going to replicate it b number of times. All right. So in step one, what we need to do, we need to compute the parameter estimates theta cap, that is theta cap is equals to theta cap of x, and then we compute the statistics of the interest. Tau cap equals to tx. All right. After that, we apply the bootstrap loop from 1 to up to capital B, and generate the random sample from the fitted distribution f theta cap, and compute the bootstrap statistic. All right. And then we compute the other inferences here. So how it basically works, we just take the example of the normal distribution. Okay. So I just before that I just explain you what is basically we are going to do in the parametric procedure. So suppose we have the observed sample capital X, that is your x1, x2 up to xn. All right. And assume that the data follows the parametric family of the distribution f theta. All right. Where theta is an unknown parameter vector and tx denotes the statistics of the interest. All right. Tx is our statistics of interest that can be either mean, okay, mean, variance, and anything. All right. And let theta cap, that is the estimate of my parameter theta, that is theta cap of x, because statistics will involve the x, be an estimator of theta such that as the maximum likelihood estimates or moment methods of moment of estimator. So the main idea of the parametric bootstrap is to replace the unknown population distribution f theta with the fitted distribution f theta cap. Okay, so we will put the value instead of theta, we will put the theta cap here. All right, so this is also known as the plug-in principle. So how we are going to do? We are going to estimate the model model parameters by using the observed data, and then we observe the statistics, that is our tau cap is equals to tx. All right, and we are going to apply the bootstrap resampling here with the for loop, and we are going to generate the bootstrap sample from the fitted parametric model. So what happened at that time? I will get x1 star, all right, of b, that is 1, x1, x2 star b, x up to x n star b, that follows the f theta cap. What is basically what I'm going to do? I'm going to generate the random sample x1 star 1, x1 star, sorry, x2 star 1 up to x n star 1, x1 star 2, x2 star 2 up to xn star 2 up to x1 star of 10,000 or whatever the value of capital B I'm going to take. All right, and x2 star B, capital B, up to xn capital star or star capital B, and these all sample will comes from the empirical CDF, not empirical, the fitted CDF of f theta cap. All right. After that, with respect to each sample, I will calculate the T cap, T1 cap, sorry, tau 1 cap, tau 2 cap, up to tau capital B cap. So I will get the capital B times capital B statistic. All right. And after that, I will use these sample statistics, tau 1 star, oh sorry, tau 1 cap, tau 2 cap, and up to tau B cap, and I will use them for my uh, to calculate my standard error and mean and confidence interval and other things. All right. So basically, what we are going to say that we are saying that the fitted distribution f theta cap will tend to f theta naught under the probability. All right. So as beta tends to infinity, the empirical bootstrap distribution converges to the true sampling distribution under the regulatory conditions. All right. So that was your bootstrap method under the parametric condition. So here we are going to take the example, confidence interval of the population mean we are going to take. So we are going to take the normal distribution problem setup. So we have the exam score of 25 students and xi that are x1, x2 up to x25. They are the marks of 25 students, and that follows the normal distribution with mean mu and variance sigma square. All right. So data summary, they are given that the sample mean is 72.5 and the sample standard deviation they have given 12.3. Now they are asking us to construct the 95% confidence interval of mu. So the classical approach says that because n is less than 30, so that is a small sample, so x bar will be, so confidence interval will be x bar plus minus t alpha by 2 and minus 1 degree of freedom into capital S standard deviation divided by uh, square root of n. So it will be 72.5 plus minus the value of t statistics from the table for alpha by 2 means that is 2.5% and 24 degree of freedom that is 2.064 into the standard deviation that is 12.3 divided by square root of 25. So what we got? We got the through the classical approach, we got the confidence interval is 67.4 to 77.58. That is the confidence interval from the classical method. Now what we are going to do in the parametric bootstrap, through the parametric bootstrap approach, we are going to take x bar as our estimate of the parameter, that is 72.5 is our mu cap, and standard deviation, sample standard deviation as the estimate of the population standard deviation is 12.3. So what we are going to do for b equals to 1, we are going to generate x1, x2, x25 from the IID normal distribution with mean 72.5 and variance 12.3 whole square. And suppose we got this data, so we compute the sample mean that say suppose 73.1. After that, what we are going to do, we are going to again generate the data 10,000 times and we generate the 10,000 means here. Okay, and after that we just find out the bootstrap standard error of those means, and then with the 95% percentile confidence interval, we got the confidence interval that is 67.68 and 77.32. That is almost similar to the that we got from the classical approach. In the classical approach, we got the lower limit 67.42. Here we are getting 67.68. Here upper limit was upper confidence interval was 77.58. Here 77.32. So here is the R code for that one. We just try in the R again. Okay. So here we are going to close the set.seed here. All right. So suppose I am having the sample. I need to generate the sample of size 25 and my mu true, the true mean is 72.5 and my true standard deviation is 12.3. So I'm going to generate the random data from the R known with the same mean and same standard deviation. All right. So this is my data, original data, not original, my data generated from the normal distribution. After that, I need to compute the estimate from the original data. So X bar I'm going to compute from the as my sample mean. Okay, because sample mean is the estimate of the population mean from under the normal distribution, and as I'm going to compute the sample standard deviation, that is the estimate of the my population standard deviation. Right. So I'm going to compute both of them here. So my sample standard deviation is 12.51 and my sample mean is 71.59. All right. After that, in the second step for the parametric bootstrap, I'm not using the set.seed because I want to see how it is going to perform when I'm going to take the different data sets again and again. So I'm going to replicate it 10,000 times. So before that, I need to store my bootstrap means in some null vector. So I'm introducing a new null vector, that is boot means a numeric b. All right. B is the number of replication, that is 10,000. So after that, I'm going to apply the for loop, and that one I'm going to generate the random numbers through the x that I'm going to store in x star from the normal distribution of size n. Mean will be my sample mean that I took from the generated data, and standard deviation will be my s, that is my sample standard deviation that I took from the generated data. All right. And after that, in the boot means I'm going to store the mean of my generated samples, 10,000 samples, whatever the 10,000 samples I'm going to generate, I'm going to store the mean of all of them in the boot means. In after that, in the next step, what I'm going to do, I'm going to find out the standard error of the boot means through the command hd, and in the biasness I'm going to compute, that is the mean of the boot means minus x bar. Right, I'm going to check that one. So boot is 2.48, boot bias is 0.0.030146606. I'm going to compute the confidence interval. So I am going to calculate the quantile of boot means for 0.025 and 0.975. All right, that is the CI quantiles I'm going to find out. This is my the quantile, percentile confidence interval. Now from the normal distribution, the command is x bar plus c minus 1 and 1 q norm of 0.975 into boot standard error. So that is my confidence interval from the normal, that is 66.73, 76.45, right? And there is a classical t interval for comparison that classical we computed earlier. All right, from the t distribution. So it is 66.42 and 76.76. So if you just see the limits, confidence interval limits are quite similar under the all three methods. All right. So these are our results. After that, now we are going to check the visualization of our bootstrap means, how it is distributed. All right. And confidence interval under the percentile. All right. So here red line is the mean of our generated data, that sample mean that we generated from the original, this one x. Okay, the mean x bar is our in the red line, and this blue dot line is our confidence interval from our CI percentile. All right, and this is our mean of our generated data. All right, these are the means from our generated bootstrap data, and this is the QQ plot to check that whether the generated means are theoretically fitted very well to the data or not. So if you just see that all the dots line are very close, or you can see the overlapping the line, the straight line, so means the bootstrap sample that we have generated, that was generated very well, and the estimates that we got, that was perfect one. All right, so now we are going to discuss about the another one, that is our exponential distribution problem. So what we are having here, light bulb lifetimes in the hours that we are having. So in the model, we are saying that x follows the exponential distribution with rate lambda. All right, and the PDF we are considering that is lambda into e raised to the power minus lambda x. We are showing the PDF because if we will change the PDF at that time, the mean will change. So the mean is 1 upon lambda and variance of x will be 1 upon lambda square, and the data that is given, that is n equals to 20, and the number of hours the bulb is functioning, that is 1200 hours. So we need to compute the 95% confidence interval of the failure rate lambda here. So the MLD of the exponential distribution that everybody knows, that is 1 upon x bar, that is basically equals to 1 upon n summation xi. All right, I don't need to find out that one. I hope all of you know that thing. So lambda cap is biased. So expected value of lambda cap will be equals to 1 up n upon n minus 1 lambda. All right, so that will be the true estimated value of the lambda cap. So in the classical method, what we are going to do, we know that the 2n nx bar divided by theta, that is our 1 upon lambda, that is 1 up into 1 up divided by 1 upon lambda, it follows the chi-square distribution with 2n degree of freedom. All right, so from there the confidence interval will be of the exponential distribution is chi-square 0.025 2n degree of freedom divided by 2nx bar, comma chi-square 0.975 2n divided by 2nx bar. All right, so that will be your confidence interval for exponential distribution. Here you will take n equals to 20 and x bar is equals to 1200. So value of chi-square with 0.025 and n is basically n is 20, so that is 40. Okay, so 2n is 40. So for chi-square, for degree of freedom 40 at 0.025 is 26.12, and chi-square's value at 0.975 with confidence with a degree of freedom 40 is 59.35. So when we are going to divide by 2nx bar, so 2 into 20 into 1200, so we got the confidence interval of lambda is 0.000545 and 0.001236. All right. So if we estimate the lambda, so lambda cap is 1 upon x bar, so it will be 0.000833. All right. So in the bootstrap approach, what we are going to do, we are going to generate the sample from the given value of lambda cap, that is 0.00833, and then we compute the lambda cap star for each bootstrap sample. All right, and then we compute the confidence interval for that one. So again we have the code here. All right. So we have the code. We have the sample of size 20, and the value of true lambda is 1 upon 1200. The true mean was 1200 hours. So we will generate the x from exponential distribution. The command is REXP, and is the sample size. Rate is the we need to provide the value of the lambda. So lambda is true lambda, that is 1 upon 1200. So we need to find out the mean of x, generated x. So here we are going to do that one. So x that we had, so we had these values of x. All right, so this will be performs as these 20 values we will use as our population here. All right, and the mean of that one, of this population, is 1000, not exact 1200, right? And lambda cap will be here now. Then sorry, so lambda hat will be 0.009992621, but we were getting the estimated mean was 0.000833. Here we are getting 0.009992621. So after that, what we are going to do, we will compute the confidence interval, classical confidence interval here. From the given method that we discussed here. All right, that we discussed here. So confidence interval, we are going to use this command to generate the confidence interval. So we use the q chi-square, quantile of the chi-square at 0.0252 into n divided by 2 into n into x bar, and q chi-square, quantile of chi-square at 0.975 into 2n divided by 2n x bar. So it provides this confidence interval. It is different because we are not using the original values. Okay, we are generating the random values from the given data. After that, for the given value of the lambda, all right, we are generating the random numbers. So after that, we are going to replicate 10,000 times again, and we are going to introduce the null vector again, boot lambda, that is numeric b. All right, so in that one, we are going to generate, in the for loop, we are going to generate the random numbers in x bar, in x star from exponential distribution. Okay, and rate lambda hat is our 1 upon x bar, that is our mean from the generated sample. And in boot lambda b, we are going to store the values of our generated sample means. All right, so this is the for loop. We just check what is the value of x bar. So this is the last sample. We generated the 10,000, but when you will call x star, so it will show you the last generated sample. So this is our last, means 10,000 sample that we generated from the given data set. All right, and boot lambda b. So here you will have the 10,000 estimates, okay, of your generated samples, bootstrap samples. Okay, so now after that, we will calculate the standard error of the bootstrap, and we calculate the biasness by using the same formula that we used earlier. So standard error is 0.000248, and the bootstrap biasness is 5.4 e raised to the power minus 0.5. So after that, we calculated the bootstrap in the biasness in the percentage. All right, that is 5.41%. After that, we calculate the percentile confidence interval. Wait. Oh, sorry. We are finding the percentile confidence interval. For that one, we are going to use the command quantile boot lambda C 0.025, 0.975. So this is for the lower and upper value of the alpha that we are going to consider, alpha by 2 here we are going to consider, and 1 minus alpha by 2 that we need to provide here. And for the basic function that we have used for the chi-square method that we have used, 2 into lambda hat minus quantile boot lambda 0.075, 2 lambda hat minus quantile boot lambda 0.05. So for both of them we have the bootstrap confidence interval, right? So that is 0.000677, 0.001625, and for the basic confidence interval is 0.000374, 0.001322. That are the confidence interval. So basically, percentile confidence interval we mostly use here in the that one bootstrap. Okay, and this is the R. This is the visualization of our generated data. All right, this is exponential. Okay, in the blue dot, you have the MLE or the true estimated value here. In the red one, you have the MLE, and sorry, in red one you have the MLE, and in the dot blue one you have the true estimated value. So it is little bit far from here. So you can find out the mean of boot lambda. We can check what is the mean of boot lambda. That is 0.001053. So here, because of the heavy tailness, here you have some very heavy tail values, so you need to replicate it more number of times. At that time you will get the exact one. That's why you are not getting the exact values, because it is quite a heavy tailness we are finding here. All right. So another example for the gamma distribution that you can check by your own. You already have the PPT. All right. So what is the difference here? Parametric versus non-parametric bootstrap. So in that one model comparison, you model assumptions that in the parametric you need the model, and non-parametric you don't need the model. Efficiency, if correct, so in the parametric efficiency is very high if the you know the model, or you know the distribution of the given data. So efficiency will be high. If you don't know the distribution, so efficiency will reduce. So robustness to miss specific specification, that is lower in the parametric, and in non-parametric it will be higher. Small sample behavior in the parametric, you don't need to struggle that much if you know the distribution, but in non-parametric you may need to you may face the struggle while sample size is very small. All right, range of the x star values, that is beyond the data. All right, because you will generate the data from the fitted distribution. So the observation that will come, that is not come only from the given data set, that will come from the fitted distribution. All right, and in that one only observed value, whatever the value you already have, the data will come from that observations only. All right, so smoothness, the parametric, in the parametric case it is continuous, and in non-parametric it will be discrete. All right, and the implementation need to simulate, and just here in the non-parametric you just need to resample again and again. So when we should use the parametric, so whenever we have the strong theoretical justification for the model, at that time we need to use the parametric inference if sample size is small, is less than 30, but the parametric distribution of the sample is given. At that time we can use the parametric, and model diagnostic confirms the fit, means model diagnostic test we have, so they will tell us that whether the data model is going to fit to the given data or not. So at that time we can use. All right. So use of non-parametric when the distribution unknown or uncertain or robustness is the priority. At that time we use the that one. So this is the template for the parametric bootstrap that I am providing you. Here you can simply change the, in the family you can change the distribution. All right. And in the data you can change the data, and after that other things will remain as it is, and then you can go for exponential, gamma, normal, whatever you want to go. All right. So that was your parametric bootstrap uh, methods. Do you have any confusion or any question here? So you can ask me. Otherwise, we will move further. Do you have any question? Okay, so we just go. We will move to the another one. That is our bootstrap methods with for non-parametric. All right. So here we will discuss the bootstrap methods in the non-parametric and student studentized bootstrap. Okay. So studentized percentile T bootstrap that we will use. Okay. So whatever the bootstrap for non-parametric we have discussed, that was the one basic explanation of the non-parametric bootstrap. We will discuss in the detail here. So what is the non-parametric bootstrap? So in non-parametric bootstrap, we make no assumption about the underlying distribution. We treat the observed sample as the mini population. All right. As I told you earlier, we use in the parametric population, we use the, we generate the data from the fitted model, but here because we do not have the distribution function of the given data set, so we use it as the population, given sample as the population, and we resample with replacement from the original data, and the empirical distribution f cap and serve as our estimate of the f. All right. So real life analogy, bags of the marbles. So you have a bag with 20 colored marbles. That is your our sample. So how we just do the bootstrapping there? We pick a marble, note its color, and put it back, and we repeat 20 times to get one bootstrap sample. And some marbles appear multiple times, and some do not appear at all. All right. So when you have the one bag of the marbles, in that one you have the marbles, 20 colored marbles. Okay. So at that time, x1, x2 up to x20 marbles are there. So when you are going to pick the marble once, so you note down the color and then you will put it back into the bag. So when the next time you are going to keep, you are not going to pick the another marble. So it is not necessary that the another marble will come. The same marble may occur again. So that you are going to do it again and again 20 times. So that will call as the bootstrap sample, one bootstrap sample, and in that one procedure you do it 20 means capital B number of times that we are saying here, capital B, that is 10,000 we are taking till now. All right, so we repeat it 10,000 times, so that is 10,000 bootstrap samples that we have. So empirical CTF that I already discussed with all of you, that was for given observation x1, x2, xn, the empirical CTF is f uh, cap n x is equals to 1 upon n summation 1 I xi is less than equals to x, that is where I is the indicator function that we discussed earlier in the previous lecture, right? And I showed you this graph also in the previous lecture when we were discussing about the bootstrap. All right, so the properties we have already discussed of the bootstrap. So now sampling with the bootstrap. So as we have discussed, so we take the sample x1, x2, xn from the uh, population that is our original sample, and we bootstrap sample x1 star, x1 star, x star equals to x1 star up to xn star obtained from the xi from the fn cap, that is for all I goes to 1 to n, that will be equivalent to the sampling uniformly from x1, x2, xn with replacement. All right, so here as I told you, the probability of each bootstrap row is 1 upon n for all n. So the number of times xj appear in the bootstrap samples follows 1 upon n, the probability. All right. So after that, bootstrap sample composition is basically the expected number of the distinct value. All right, expected composition of a bootstrap sample. The expectation is basically n into 1 minus 1 minus 1 upon n raised to the power n. That will be equivalent to the n into 1 minus e raised to the power minus 1, and that will be equivalent to 0.63 n. All right. And this is the probability that value will occur, different value will occur in the your bootstrap sample. So that is the expectation of the different value will occur in your bootstrap sample, that is 0.632 into n, and the probability that the observation xj is not in the bootstrap sample is 1 minus 1 upon n raised to the power n. All right, because if you remember that one, I told you in the previous lecture that x give me a second. If you just remember in the previous class, I told you that uh, n into f and cap x is following the binomial distribution with parameter n, and probability of success is f and x. And here, as we define that fnx is 1 upon n, the probability of one sample will select in the data set, that is 1 upon n. So at that time, the probability that it will not uh, selected in the given sample, it will be 1 minus 1 upon n raised to the power n. So it will be, as n tends to infinity, it will be e raised to the power minus 1. That will be equivalent to the 0.368. All right. So this is the mathematical property. If you know that, I don't know how many of you know this. Anybody know this property of the exponential? Anybody knows this property? Okay. Okay. So the property basically, it says that if the property is basically as limit n tends to infinity, okay, 1 minus 1 upon n raised to the power n, okay, it will be equals to or equivalent to e. All right. So that is the basic property of fundamental limit property in calculus. Okay. So from that one we have, when in the n is in the denominator and n as well as in the power, so we can write it as the e equals to e. All right. So sorry, not e. It is basically 1 upon e. All right. So that is equals to 1 upon e. So that's why it will be equivalent to e raised to the power minus 1. So that is the fundamental theorem from the calculus. Okay, so from there we are writing it as n tends to infinity, 1 minus 1 upon n raised to the power n will be equals to e raised to the power minus 1. So equivalent to 0.368. So if n is enough large, at that time the probability that the observation xj will not select it to the bootstrap sample, that will be 0.368. All right. For example, about 63 unique observations appear in the bootstrap sample. About 37 observations are left out or out of bag samples. Means 37 observations are not appeared. All right. So some observations appear 2 or 3 or more times, like that if it is happening. So that is the basically expected composition of a bootstrap sample. So in how non-parametric bootstrap algorithm, how we are going to generate the bootstrap sample. So in that one, our goal is to estimate the theta cap, that is equals to t x1 x2 xn. Here t x1 x2 xn is our estimator of theta. So how we are going to do? We are going to compute the original estimate theta cap from the tx, and we will draw the, after that we draw the n observation with replacement from the given samples, and call these samples, that will be called as the bootstrap sample, and we compute with respect to each sample that I showed you here. These one here they were following the some distribution, but here they will not follow the distribution, but still they are the bootstrap sample. And for these samples, I am going to compute the Tx star B and analyze the bootstrap distribution of all these theta 1, theta 2 up to theta cap star B. I'm going to evaluate them. So here we sample directly from the data, not from the fitted distribution. So here we are going to take the example bootstrap of the median. So scenario is that median salary of the employees in the department. Okay. So suppose n equals to 10. 10 of samples we are having, and the salary in the thousands. So I'm not writing in the thousands, I'm writing only 45. Instead of 45,000, I'm writing 45. Okay. So I'm just shifting the origin by subtracting by, oh sorry, I am changing the scale by dividing all of them from the thousands. Okay, so it will be 45, 52, 48, 61, 55, 49, 58, 47, 63, and 51. So I will find out the original median. How we find out the median for the given data set? What is the formula to find out the median? Do you have any? Do you remember that one? We need to sort the data in the ascending order, and then if it is odd number, so n plus 1 by 2th observation. If it is odd, if it is even, so n by 2 2th observation plus n by 2 plus 1th observation divided by 2. Right. So here we are going to short the data. So when we are going to short the data, how it will be, observation will look like. 45 is the minimum, then 47, then 48, then after that 49, if I am not wrong. 45 is done, 47 is done, 48 is done, 49 is done, 49, then 51. Okay, after that 52, then 55, sorry, 55, then 58. So how many are there remaining? 61 and 63. 61 and 63. So observations are 10 observations. So it is a even number. So n by 2, that is fifth. 1, 2, 3, 4, 5. Fifth observation and sixth observation divided by 2. So that's why 51 plus 52 divided by 2 equals to 51.5. That is the original median. What is the standard error of the median? If I am going to ask you, what is the standard error of the median? So no simple closed form formula exists for the median to check the standard error. So what we are going to do here now, we are going to generate many bootstrap sample and compute the median for each, and then we find out the standard deviation of the bootstrap median. That will be the standard error of the estimate. Okay, so here we have the code for that one. Original data is given that, then bootstrap sample, in that one we are going to generate the first bootstrap sample and we are going to short it, and then we find out the first median, that it comes 50, and again we are going to generate the second bootstrap sample from the original data that is given here. Okay, and we are going to short it again, and then we are going to find out the second median, that is 53, and we are going to do it again and again and again, and then we find out the standard error of the medians, that was the standard deviation. It is 3.2. For that one we have the R code given here. Okay, let me check if I am having the R code for bootstrap. Okay, so I just check here. So we have the original salary that is given in. We store in the data set that is in the salary only. So n is the length of the size. So original median, we are going to compute the median of the salary. All right, the command to generate the median is directly median in R. So we computed the original median that comes as 51.5. Okay. After that, we are going to use the bootstrap. So set.seed we have command we are going to use. But if you want, you can remove that one. So B, the replication of bootstrap we took as the 10,000, and we will get the 10,000 median for 10,000 samples. So we are going to store them in the boot median command. That will be numeric B as a null vector. After that, we are going to resample. So boot sample, in the boot sample, we are going to generate the samples from the salary of size n, and we are going to replace the values so that replacement is true. After that, we are going to store the medians in the boot median null vector. That will be median of the boot sample. All right, so we are going to run this one. Okay, now we are going to call the results. So original median was 51.5. So, and the boot medians I just call. These are my boot medians for my samples. 10,000 boot medians. Okay, and now I just find out the bootstrap standard error, that is 2.82, and bootstrap biasness of the median is 0.529. Okay, and now confidence interval, that is quantile boot medians, the same function we are going to use. Okay, that we were discussed earlier, that is 48 to 58. That is the confidence interval of the median. We do not have any formula for the confidence interval and standard error for the median in the closed form in the theory, but we can find out it through the bootstrap method. Okay, so that was the bootstrap. Now we just talk about the correlation coefficient. In that example, we have the 15 students and we have the data of number of study hours in X, how many hours they are studying, and the exam scores we are storing in the Y, that is 65, 72, 78, and so on. And sample correlation that we find out, that was 0.73. After that, the question that arises here, it is, what is the 95% confidence interval of the true correlation coefficient? All right. So classical approach to find out that one, uh, confidence interval of the correlation coefficient. We have the Fisher's Z transformation, that is Z equals to 1 upon 2 log of 1 plus R divided by 1 minus R. R is your sample correlation coefficient, and standard error of Z, that is 1 upon square root of n minus 3. Okay, the problem is that assumes bivariate normality, means both of data are normally distributed here. That is the problem. But in the real life, it it is not necessary that both data sets are normally distributed. All right. So at that time, this method will not work. Okay, if the both data sets are normally distributed, that time you can use these methods, this Fisher's Z transformation method, to calculate the confidence interval, but otherwise you cannot use. So here what we will do, we will resample the pairs xi and yi together, and original data pairs we just take x1, y1, x2, y2 up to xn, yn. And for each bootstrap sample, we draw the n samples with replacement and compute the correlation of bootstrap pairs again, and use the bootstrap correlation for the inference. Okay. Yeah. There is a one important thing. Never resample x and y separately. This destroys the relationship. Means if you will generate it again, so what happens? The combination should remain as it is. All right. Means when you generate the study hours 2, the exam score 65 should be there. Okay, it should not look like that. When you generate the study hour 2 and 78 or 82 exam score will should occur. It should not happen. All right, if it is going to be you are going to separately, you are going to resample them. So at that time, what will happen? It will impact your final results. All right, so what we are going to do? We are going to check in the R. Okay, so here we have the data. N is equals to 15. 15 students are there, so their study hours are there, and we are going to store them in the study hours. And exam scores, corresponding exam scores are there, so we have the corresponding exam scores here. So we are going to find out the original correlation coefficient. For that one, the command is core, to find out the correlation coefficient of the given data. So correlation coefficient of the original data is 0.9783248. Right. So after that, what we are going to do here, uh, we are going to do the bootstrap resampling pairs. So we are going to replicate 10,000 times again, and we are going to save the correlation in the boot course null vector, okay, by the command numeric b. All right, after that we are going to apply the for loop here, because we need to generate both of them together. So first of all, we need to find out the samples 1 to n. Okay, sample 1 to n and replace is equals to true. Okay, so sample indexes we need to generate here. We are generating the sample indexes. After that, what we are going to do? We are going to find out the boot correlation uh, by using the command core, and in that study hours IDX indexes we are going to use. Okay, and exam scores IDX, the index, same index we are going to use, whatever the index will come. Okay, suppose here so index. So this is the index 10, 8, 9, 4, 1, 5, 6, 15, 3, 10, 6, 3, 8, 10. So how it will work? So now study hours and exam scores we are going to run. So if we just see here, index 10, so it is taking 2 study hours, so 60 is come for the that one. What is this? No. Because of the replication, it is problematic, because it is coming in the that one last value, so that is not correct. Otherwise, they are going to come in the pairs only. All right. So some problem is there because of the loop. It is not showing correctly. Otherwise, they should be comes in the same manner. All right. So we just check original coefficient, that is 0.978. We check the bootstrap standard error, that is 0.01, and we compute the bootstrap confidence interval by using the quantile function of the boot correlations. And in the C, we are going to take the alpha's value 0.025 and 0.975, and it will be 0.954 and 0.992, and we check the correlation, bootstrap correlations for all the values. These are our bootstrap correlations. Okay, so that's how you can compute your bootstrap standard error and bootstrap confidence interval. Okay, for different statistics, correlation, median, and another example is here for bootstrap for the variance. Okay, that we will discuss in the next class. If you have any question, you may ask right now. Do you have any doubt in this one?